my task here is to teach you guys quantum mechanics as well as I can in 3 weeks. So you've all had some quantum, and what I'm probably going to do is do everything from scratch, but do everything at a very high level. So hopefully it'll involve a generality that you may not have seen before, at least in some aspects of describing quantum theory. I certainly hope that I can answer all of your questions. Quantum theory is, for the most part, mathematically easy, but I think conceptually very subtle. And there are lots of nuances that you have to kind of come to the grips with. And sometimes seeing things explained in different ways helps. I know that when I took quantum mechanics in undergrad, I was so dissatisfied with the lectures that I went and just got the entire shelf of library books on quantum mechanics at the library and just started reading them all to try and find a more satisfactory explanation of what quantum theory was telling us. Didn't find one, and so now I find myself here. More or less devoted my career to understanding quantum theory. So I really hope that I can impart as much of that as possible to you guys. I'll tell you a little bit about myself. So my name is Joseph Emerson. So I'm on the faculty at the Department of Applied Mathematics at University of Waterloo. I'm also a faculty member at the Institute for Quantum Computing. So yes, when you've been doing quantum mechanics for some 20 years, it just becomes Q every time I write it. What else can I tell you about myself? So I started my career, I did my PhD under Leslie Ballantyne at Simon Fraser University. We studied quantum chaos and quantum foundations, and in particular, how to understand chaos in quantum systems and how to understand the emergence of classical chaos in the kind of classical limit, how to reconcile the nonlinearity of classical chaos and the linearity of quantum theory. And then I did a postdoc at MIT. I switched fields to quantum computing. In particular, I worked with an experimental group, David Corey's experimental group, that did the first implementations of quantum information processing using nuclear spins. There, my goal was to understand what kinds of interesting experiments they could do, help them understand how to characterize the level of precision and control they had in implementing the states and transformations and measurements they were trying to implement. Then I did a postdoc here at Perimeter Institute for 2 years, working still at the interface of quantum foundations and quantum information. And then I started my faculty position after that, which is I'm just right across the pond here at the University of Waterloo, which hopefully you all get a chance to come visit us at IQC sometime. We just got a nice new building about 8 months ago, and it's a pretty lively and active place to do research. So let's see, what's next? Basically, I want to kind of try and convey what I think is interesting about quantum theory. Why is it something that you want to study well as a theoretical physicist or as an experimental physicist? I should mention also that I did my PhDs, all my degrees were in physics. So at some point I became too mathematically precise, so I got hired by an applied math department. But really, as you'll see from my lectures, my style of thinking is very much a physics way of thinking, and the math is just to make sure we get everything right at the end. So what's interesting about quantum theory? So basically, you all know about the conceptual puzzles of quantum mechanics. I kind of was toying with the idea of going into philosophy as an undergrad, and so I was very much interested in understanding what can we say definitively about our place in the universe. What is the nature of reality and so on? These are very deep questions. What's remarkable is that a scientific theory like quantum physics can actually give us insight into what is and is not possible for understanding those very profound questions. From the point of view of a physicist, we're very much interested in physics. I see as very much being about the prediction and control of systems. So the point of our formalizing physics as a mathematical theory is that we can make predictions about those systems, verify them experimentally, which validates the theory, And then from that, we get an advantage. We can leverage that to our social advantage, right? So there's all kinds of social reasons why we want to have the ability to predict and control systems, whether it's the planets or condensed matter phenomena. So quantum theory has been an enormously successful theory on that level. Can maybe you guys just mention some of the major technological advances that came from being able to have quantum theory as a tool to analyze physical systems? Yeah, that's true. So a lot of the analysis of microcircuitry is based on studying the solid state of materials like silicon, gallium arsenide, things like that. You need quantum theory as a tool to analyze the band structure, to understand the functioning of the p-n junctions, the underlying transistors, which are, are the primitive, the scientific primitive underlying microcircuitry. What are other examples? Medical imaging. It's a great example. Maybe I should write some of these down because this is a good list. I'm still waiting for the whiteboard to dry. Well, I guess I should start on the top one anyways.
Bottom left corner.
No. Oh, that is right. Okay, good. So we have solid-state physics and modern microcircuitry. Hope I spelled that right. You know, the p-n junction is controlled by the quantum band structure of condensed matter materials. There's medical imaging. So here we have, for medical imaging, MRI. MRI is based on controlling nuclear spins. The description of this is very similar to the way they do quantum information processing with nuclear spins. Except in the quantum information processing setting, you want to control the interactions between spins and not just control each spin separately. Medical imaging, there's a lot more than that, right? I'm not a biophysicist, but CAT scans? How do CAT scans work? I don't recall. It's X-ray, so that might not require quantum. I mean, certainly X-rays are produced by quantum transitions, but yeah, that's a good one. Well, we're trying to be too redundant. Things that are just based on solid-state physics, I mean, we don't want to double count, right? Anyways, I'm sure there are others. What else? What makes your DVD player work? All right, lasers. Very quantum mechanical phenomenon. Anything else you can think of? Yes, that's arguable, but sure, let's go with that. Okay, well, anyways, I mean, I'm trying to give you a flavor of all of the wonderful things that we've achieved technologically because of quantum theory. There's also things like nuclear power. In particular, it's the variation that gives us, electricity. And what else? I'm sure there are others. Not all coming to mind right now. But you can construct a very long list like this. Oh, superconductivity. Which superconductivity hasn't really had that enormous practical breakthrough that we get with high TC superconductivity. But I mean, I think we're on the road towards widespread technological applications of superconductivity, pending some hurdles. Okay, good. So let's just tie that there. So on the one hand, we have practical applications. On the other hand, we have fundamental reasons for studying quantum theory. Okay, so quantum theory is probably the most successful theory ever developed by scientists. Successful have two S's or one? Thank you. Most successful theory ever devised by science. So what do I mean by that? Well, on the one hand, I mean that the scope of phenomena that have been predicted and verified for quantum theory is enormous. So there's an enormous variety or scope of physical phenomena so again, everything from atomic physics, precision atomic physics tests, to quantum optics and lasers. What else? There's nuclear phenomena. There's solid state and other condensed matter. Systems whose phenomena, like superconductivity, are explained well by quantum mechanics. And in some sense, we recover all the predictions of classical theory, all the macroscopic predictions of classical mechanics. I'm putting all in scare quotes here because, I mean, I studied the quantum classical correspondence for my PhD, and I think the problem is it's enormously difficult in some circumstance to even see what quantum mechanics is predicting in certain macroscopic situations. So I wouldn't say that we have a comprehensive verification of the classical limit, but and there's some interpretational issues that come into play there. But let's say we know of no problems. We know there's no known problems of classical / macro, well, I already said macro, of classical mechanics. And then the other, and of course this goes on, right? I can just put 3 dots here. And the other sense is these high precision tests. What's remarkable is there's certain experimental situations where you can measure certain fundamental quantities to very high precision and compare them to experiment. And here, quantum mechanics has always worked. High precision tests of quantum theory. So an example is measuring the fine structure constant, which I think that the best known experimental value for this is, so this is the fine structure constant. 137.0.35990.070, and we have 98 as the error bar on this number. Thank you. And then the point is, theory and experiment agree to 1 part in 10 to the 8. So that's remarkable. I'm not familiar with the situation with general relativity, but I imagine there are corrections that come close to this that have been calculated and measured. For example, for the GPS, timing of GPS satellites requires general relativistic corrections. I think that's actually the only known experimental, practical application of general relativity, is getting precise GPS timing, which in turn gives you precise location measurements with your phone. Okay, and so fundamental reasons, I guess maybe I should start numbering things. So this is A. And then within other fundamental reasons, we have so does anyone know the next button I have to press? So you do a circle counterclockwise?
1, 2, 3, 1, 2, 3.
Great. Okay. So part B here is, I think, is going further. Or is it farther? So basically, we have this problem, which is that we have this beautiful theory called general relativity. Works great in the regime where it's supposed to work, which is describing, large-scale, massively interacting objects. And we have quantum theory, which works great in the regime where it's supposed to work, which is small-scale phenomena. We believe that quantum theory is also true for large-scale phenomena. That ties in with this recovering the predictions of classical mechanics. But there's, oh, there you are. I didn't see you there. But there's some issue of reconciling quantum theory with gravity, right? So I don't know of, other than maybe black hole evaporation, we don't really have hard data on the constraints for reconciling these two theories. So it's more of a theoretical motivation. But for black hole evaporation and other situations where you have very massive objects interacting on scales where quantum theory is important, it's not clear at all how to correctly describe those systems. Do you take a curved space-time that you get from general relativity and just do quantum theory on that curved space-time? Or do you have to change quantum theory in some way to make it work with general relativity, or change general relativity? These are all open questions, and this is something that's studied here intensively. But my personal view is that we don't have enough information about the best way to go tackling that problem. And I think that getting deeper conceptual insight into quantum theory, what kind of theory is quantum theory? What does it tell us about the world? The question of hidden variables and interpretation. These issues are, for me, important because I think they will point to the right way to solve this, what's been basically an intractable problem for almost a century. So I think a deeper understanding of quantum theory is essential for finding the right path to unifying quantum theory with gravity. There's one more thing I wanted to say. going further, I'm going to do a subpoint 1. I'm going to do a subpoint 2. So when it comes to any theory, any scientific theory, the whole premise is that it makes falsifiable predictions, and those predictions can then be verified experimentally or refuted experimentally. And so we certainly know how to do that with quantum mechanics. We have a mathematical formulation of quantum mechanics, which we know how to use, and which tells us how to make predictions in the lab, how to compare those predictions with experiment. But we don't have, again, this conceptual understanding of quantum mechanics, which on the one hand, I hope will be useful to resolving this enigma of reconciliation with general relativity. But on the other hand, we can ask the question, what can we do now with quantum theory that we couldn't do without it? How is quantum theory useful? So my favorite example of this is quantum information. Yeah?
Just a question. I mean, it's we often talk about how we need to unify gravity with quantum mechanics, but do we even know it, like, mathematically, is that always possible? Like, can it work as a consistent algebraic system? Do we know that it has to work like that?
No, we don't know.
Okay.
So what I wanted to get at, though, was the power of quantum information. So here's something where we had quantum theory. We've had a mathematically precise formulation of quantum mechanics since von Neumann in 1930. That was the first time someone wrote down a consistent mathematical formulation of quantum mechanics. That was 83 years ago. It was only about 20 to 30 years ago that scientists realized that, well, hey, we have this quantum theory. What can we do with it? We can actually solve problems in a computational framework. We can solve problems in a communication framework which can't be achieved using only classical information methods. So there was this conceptual insight very, very late, whatever it was, 50 years later since the development of quantum theory, that this theory would enable possibilities in information processing and communication that aren't possible without it. So why that enormous delay? So in my view, that enormous delay is in part because of the lack of a deep conceptual insight into what quantum mechanics is about and what it enables. So this is just an example. And then, of course, superconductivity is another example. There are many others. And then my question to you guys is what next? What else can quantum theory do for us that we haven't realized yet? And I think that a good way to kind of brainstorm about this problem is to start by having a deep understanding of the different conceptual pictures that are possible about the world in light of quantum theory. And so we'll touch on some of those issues in this class. It's something I do for research, but I think Lucian Hardy will be teaching a course on quantum foundations which will explore these issues in greater depth, and I highly encourage you to take it. Okay, so that's, I think, a summary of the major points I wanted to touch on, and then we can just launch into looking at a mathematical formulation of quantum theory axiomatically, and then build on that. Have you seen any kind of outline for the course for what's going to be covered this next 3 weeks? Okay, so I'm going to be following roughly what I did last term. But before I do that, do we have any particular questions about some of this motivation? Or if there are burning, well, let me give the outline, and then I can see if you have burning topics you want to just explore that aren't listed. So we're going to cover basically axioms. We're going to discuss composite systems and entanglement. guess this will include things like von Neumann entropy, and other criteria for entanglement. Theory of measurement. Decoherence. Abstract formulation of quantum versus classical mechanics. Particularly this will involve Poisson brackets. One of the things that people who care about these things often get disturbed by is the fact that we have this mathematical formulation of quantum mechanics, but it's very different from the kind of principled derivation of things like special relativity, where you say, okay, well, let's assume the laws of physics are the same in all reference frames. Let's assume the speed of light is constant. And then, boom, this elegant mathematical theory falls out of those assumptions. In quantum theory, we don't have that kind of situation. We start talking about Hilbert spaces and density operators and projective measurements, and then we have this recipe, right? And so there's this kind of long-standing question for which we've had partial progress in the last couple decades of understanding how can we deduce quantum theory from a set of physical principles. This, in fact, I should have mentioned here, which is which physical principles imply quantum theory. And this, of course, feeds back into points 1 and 2 here. Yes?
My question is related to that. One thing that I've always wondered is, what metaphysics does quantum mechanics presuppose? Like, does quantum mechanics require us to believe a certain metaphysics about the world, like studying in philosophical terms?
So quantum physics is, unfortunately, currently consistent with several metaphysical pictures of the world. Here I'm loosely interpreting metaphysical to be some kind of interpretation of the quantum state. And so there are currently probably 4 or 5 viable points of view, interpretations, which are held by a significant fraction of the community. So the community is very divided on that topic. And I mean, that's a subject I could go on in great length about. But so the point is, it's an open problem. It's an open problem, and it very much ties into this kind of what kind of theory is quantum theory? What does it tell us about the world? There are several known solutions which are satisfying to some people, unsatisfying to others. There are probably other possibilities we haven't even considered. And I think kind of having the right picture could help substantially with this quantum gravity problem, also with conceptualizing about what kind of capabilities does quantum theory buy for us. Probably my favorite allegory on the value of these questions, though at PI one hardly has to justify these things, but in the broader scientific community, people are like, look, we have the theory, it works. Why are you worrying about its interpretation? And here's what I would say to them. Einstein struggled with this question of interpretation, Schrodinger as well, and others, and they had these debates. And Einstein was trying to come up with arguments to justify why some interpretations were just not viable, in particular the ones that take the wave function to be some physical object. And in what he found as a crucial element which allowed him to do that, to show that assuming the quantum state is physical is implausible, was to look at entangled states and invoke this notion of locality, that, well, 2 objects are space-like separated, they can't influence each other. And so what he did is made an argument, the EPR argument, with Einstein, Podolsky, and Rosen, and they showed that, okay, well, if this is the case, then these kinds of interpretations are not viable. And then 30 years later, Bell showed that, well, look, if I consider these entangled states, which are interesting only from an interpretational point of view, then I can also show that, in fact, a larger family of interpretations, local hidden variable interpretations, which Einstein hoped for, are actually inconsistent with the predictions of entangled states by deriving an inequality which quantum mechanics violates. So here, these questions of interpretation, which relied on the use of entangled states, ultimately pointed to the fact that there's something very special about entangled states. When you try and interpret tangled states in a way that seems natural classically, you find that you cannot do that. You cannot be consistent with quantum theory. And then, 20 years later, 30 years later, we realize that, well, actually, entangled states are a resource which allow us to achieve things in terms of quantum communication that cannot be achieved with sharing classical bits. So here, for me, the compelling story is that worrying about which aspects of quantum theory can and cannot be understood from a reasonable classical point of view gives us insight into which aspects of quantum theory are actually empowering and enabling for solving practical problems. So that, for me, is a strong justification beyond these kind of more high-minded concerns about building theories. This ties in really with the practical issues of, what can we achieve with quantum theory, which I guess is this point 2 here as well. So yeah, so the point is it's an unsolved problem, and we'll touch on that, and I'm happy to talk about that kind of after lecture and so on, because it's something I care about deeply. Okay, so where are we? Right, so this abstract formulation of quantum versus classical mechanics, this is something that people don't normally see, and it's kind of one of my favorite insights into understanding what is similar and different between quantum and classical mechanics in terms of a very abstract mathematical formulation. And so we'll get to that. We'll touch on that. Oh, well, here, and the next topic is actually interpretational issues. Interpretational issues. EPR, paradox, etc. Actually, I got these out of order. This is supposed to come before this. Oh, well, here, I guess this numbering scheme is somewhat arbitrary. Bell's inequalities. I mean, this could very well be under subject 5. Let's just do it that way. As you're starting to see, I'm sure the emphasis here is not on problem solving, but on getting the right kind of mathematical and conceptual framework for understanding quantum mechanics. Okay, then we'll talk about infinite dimensional. The only part that's mathematically hard about quantum mechanics is dealing with infinite dimensional Hilbert spaces. The rest is just linear algebra. Infinite dimensional systems, path integrals. The path integral formulation. We'll talk about then, I guess, a little bit of applications, time permitting. Simple simple applications. And then we'll talk about simple applications and open systems. Does anyone know what I mean by open systems? How many of you have come across that in the context of quantum mechanics? Sorry, the background noise was too loud. Yeah, exactly. Yeah. So the idea is that, look, quantum mechanics, we're going to look at its ideal formulation, which assumes that you've done a perfect job of isolating it from other quantum systems and so on. In practice, that's never true. And so you need some way to mathematically account for what happens when the system is not closed, meaning the system you're trying to control and manipulate and measure has residual interactions with other quantum systems. How does that impact the dynamics? And so there's a way to analyze all of that. And that's something I also do for research. So that's something I know very well.
I have one question about the first part of the outline. You're talking about entanglement just for bipartite systems, right?
We'll probably only cover a bipartite case. What am I on, 10? The final thing is examples from quantum information. So as time permits, we'll talk about quantum teleportation, and other kind of apps. E.g. factoring. We won't derive Shor's algorithm, but we can just talk about it. So it's an important thing. A little more detail and Shor's algorithm. Okay, good. So now, I taught this course last year at Psi. I've been teaching quantum mechanics for 6 years now, almost every year, to varying levels, usually fourth-year undergrads and first-year grad students. So it's exactly you're exactly in what I'm used to in terms of background. The Psi program is especially diverse. So what I noted last year when I gave the lectures is that there was a big gap between the preparation that the most prepared students had and the least prepared students had, which is unusual. At the university setting, you usually get a class of students who have all taken more or less the same courses, so you know what they know and you know what they don't know. Some students will self-study, of course, but you can basically address the common, the common denominator is big. But so here it's going to be very broad, and so it's a challenge for me as a lecturer to kind of make sure that you're all getting something out of the lectures. So the best way to achieve that is for you guys to give me lots of feedback. Anonymous notes are fine, but just, put up your hand and say, I don't know what you're talking about, or this is boring, we know all this, all right? I won't be offended, because I understand that there's a breadth of students. The other problem is that, if the student who's had the most background in quantum mechanics, every lecturer says, well, look, this is boring to me, but, half the class says, well, we've never seen this before, then, obviously I can't accommodate everyone perfectly, right? So we'll have to find a balance. So please be vocal, and I'll get a sense of what the right level to address the lectures to is. But please do be as interactive as possible. It shows me that you care and you're interested, which makes me give a better lecture, and it helps everyone all around. So don't be shy. Okay, so that said, from these topics, is there anything here that you want to say that's especially interesting, or something not on here that you would really love to see because it's been bothering you for however long it's been you've been studying quantum mechanics? So please just throw out things, and I can adapt these lectures to cater to your interests. So please tell me now what you'd like to hear, and I'll try and find a way to work it in.
Second quantization?
Okay, that's a great topic outside of the scope of the course, unfortunately. But maybe I could touch on that at the very end. I'll look into it.
When when you discuss interpretational issues, will you give alternate mathematical formulations of quantum mechanics as you address them?
Okay, so let's be more clear there, because so let's talk about terminology. Okay, so most interpretations of quantum theory are just another mathematical formulation of quantum theory, in the sense like de Broglie-Bohm has its own way of describing quantum phenomena. There are some interpretations which aren't really interpretations. So this question of the classical limit is critical, because very, very famous scientists, Nobel laureate winning scientists like Tony Leggett and others, believe that the problems of interpretation are so severe that it must be that the actual mathematical formulation doesn't work at macro scales. So that is not so much an interpretation, but a alteration of quantum theory. So one introduces nonlinear terms in the dynamics and so on that are associated with spontaneous collapse of the wave function. In my view, though, that's a very misguided way to approach the problem. And so I probably won't touch on that. But I will touch on the interpretations which I think are compelling and what's compelling about them. So certainly you'll see that. I know there was more originally, almost the same thing, or yeah.
When you're talking about the abstract formulation, are you going to go over manifolds and symplectic forms, stuff like that?
Symplectic forms come in. Manifolds, I guess, could come in, but don't have to. It's probably only going to be like a lecture, so it'll be. I'm not sure exactly what geometric quantization refers to. No, the abstract formulation of it's basically I'll tell you what it is in 2 sentences, and you get a whole lecture on it in a few weeks. The idea is that you have classical mechanics, which you think of as Newtonian mechanics. You have a phase space. You have dynamical variables. They evolve in time deterministically, but non-linearly. Then you have quantum theory, where you have a Hilbert space. You have the Schrödinger equation. You have a wave function, which is an element of the Hilbert space. It evolves under a linear differential equation. So those are very, very incompatible frameworks. So what we do is this. We look at the von Neumann equation for quantum mechanics, which is basically a Schrödinger equation, but it allows a broader description of situations where you don't have perfect information. And then we compare that to the classical situation of incomplete knowledge, which is the Liouville mechanics. So how many of you have seen Liouville mechanics? Very few of you. It's like a chapter late in, what's his name's book? Goldstein's classical mechanics book has it. So that's the kind of the standard classical mechanics book. But basically what Liouville mechanics is this. It says, look, sure, I can talk about Newtonian or Hamiltonian physics where I have a point in phase space. But in practice, I never actually know exactly what the point in phase space is. I only have some information about the possible locations of that point. So I really should describe my knowledge in principle as being a phase space density with finite support on the phase space. And then I can ask, what is the equation that guides the evolution of that? And it turns out that Liouville solved this problem 130 years ago, and it's the Liouville equation. And it's basically identical to the Schrödinger equation in the sense that you can write them both down in this mathematical framework using a bracket called the Poisson bracket, which you can just think of it as an object that takes 2 inputs and gives you 1 output and follows certain rules. The Poisson bracket, and you get this differential equation for the time evolution of some function in terms of this Poisson bracket. And then what you do is you say, now look, my Poisson bracket corresponds to the Hamiltonian and other observables in the system. Those are the arguments that go into the Poisson bracket. Then I ask, well, look, what is the algebra of observables? If my algebra is non-commutative, then I find there's a unique representation of the Poisson bracket in terms of the commutator. And then I get the Schrödinger equation falls out. If, on the other hand, I assume my algebra of observables is commutative, then there exists a representation of the Poisson bracket as the classical Liouville equation. So what I have is the same mathematical formulation, and then one condition, the question of commutativity of my algebra of observables, determines which theory I get. So for me, that's a very elegant formulation of both theories in the same language where you recover one theory or the other, and then you just do representation theory to get quantum mechanics or to get classical mechanics. So it really is a very natural way to think about both theories in the same setting. So that's what I mean by this Poisson bracket picture. And certainly what happens then is that when you look at the classical picture, you get a symplectic flow on the phase space manifold. Quantum mechanically, you get a time evolution equation for a vector in a Hilbert space. But that's representation theory that buys you that, as a consequence of the assumption about the algebra of observables. So that, for me, is the best way to think about quantum mechanics and classical mechanics in the same mathematical picture. And then you see how the mathematical differences arise as a consequence of a simple principle. So that's what I'll cover there. If that was too fast, don't be too intimidated. That's a whole lecture in 2 minutes.
Maybe another question. Somewhere in any lecture, are you going to refer to indistinguishable particles?
Oh, yeah, actually, sorry, that's one of the mandated topics I'm supposed to cover, I believe. Yeah.
Going to mention anything about how does entanglement work for this type of particles?
No, I could actually. That's worth considering. So I'll try and fit that in. Yes.
Do you have like a standard reference here you're using or anything?
No. So I'm a very peculiar person, so I have my own custom notes on quantum theory, which I've actually written. I mean, these are all like LaTeX. This is actually my introduction to quantum theory for the Open Quantum Systems course I teach at the university. And so there's a large overlap of material, but most of these lectures I'll be picking pieces from different lectures I've given and combining them. I'll figure out some way. I'll coordinate with Aggie and figure out the best way to give you guys. But I mean, I haven't seen the cameras moving around, but in principle, these are recorded, these lectures. Is this being recorded? I haven't heard the little motor moving around as I pace. So I don't know. Are they following? Maybe they're quiet now. Or they used to be really. Oh, I see it moving over there. Okay. Okay. So these lectures are online, and so that's a pretty good starting point. And I'll see if I can put something else together. Shall we get started, or is there any other burning issues you'd like to raise? It doesn't have to be burning, but all right, we'll get started. Okay, so now don't be disappointed, but you're going to get 3 axioms, and you're going to have this impression that somehow we can reduce quantum mechanics to 3 axioms. That's totally misleading. In fact, there's probably another 15 kind of auxiliary axioms we have to assume to actually use quantum theory. And I don't know the best way to make this distinction, but there's kind of the basic axioms, and then there's the additional side information you need to use quantum mechanics. But we'll get to that in a moment. So let me just start with axiom 1. Let's give a nice section title, axiomatic formulation of quantum theory. Wow, it's very concise. Okay. Fairly pithy. Okay, so for those of you hoping that I would say something like a quantum system is a state vector, that's not what you're getting. What you're getting instead is an operational notion. So when you deal with fundamental questions of interpretation and so on, the word state is like the worst word to use in any discussion because it means so many things to so many different people. And so we just try and just banish that word altogether in any kind of formal discussion about making sense of quantum mechanics. So here I just talk about a preparation. So let me talk about the conceptual framework, and then I'll describe some of this terminology. So the conceptual framework, the conceptual approach is an operational approach. Is an operational paradigm. So what do I mean by that? What I mean is that when I'm going to test quantum theory, what am I going to do? Well, I'm going to have some device in the lab, which here now is just a black box. In fact, let me use another board. So here's the operational paradigm. I have some device, and that device has a knob on it with a pointer. And then I have little hash marks, and I can turn this knob, right? So this is a knob that I control. And then I have a little button here which you can push, and this is the go button. And then what happens is that there's this exit port on this box. And then when I press go, some invisible object leaves this port. All right, I'm not going to say anything about that object. And then I put another system here, another box. And this has an input and an output port. And this box has another knob on it, and another set of knob settings. And then this is a preparation. And this is a transformation. So the object comes in, and then it comes out, we imagine. And then we have another box here, which has two settings. It has a knob where I can choose some setting, and it also has a readout. So this is the readout. And this is slightly redundant, but I'll put a little light on here. And this is a flash. Okay, so what I find is this. The needle has some rest position. I choose this dial setting, I choose this dial setting, I choose this dial setting. And then when I press go, this light flashes, and this dial assumes some value, this pointer. And I get some outcome. And here, let's label these outcomes by an index k. So I get some readout k. So k can be a continuous variable, it can be a discrete variable. And that's my experiment. And now what I want to use is I want to be able to do this. I want to be able to, given a choice of knob settings, when I press this button, I want to be able to predict where this needle is going to go. Quantum theory does not do that for us. Quantum theory does not tell us where the needle is going to go under generic circumstance. What quantum theory tells us is if I repeat this experiment 1,000,000 times, or 10 million times, or even just 50 times, quantum mechanics predicts the probability of this outcome being indicated on the apparatus. So quantum theory makes probabilistic predictions. Now, there's certain situations where I can predict exactly what outcome will happen. Does anyone know what that is? When does quantum theory allow me to do that? Okay. Yeah, exactly. So if my measurement if my preparation happens to be an eigenstate of the measurement operator, so here this dial is picking out different measurement operators, then I will indeed be able to predict exactly which outcome will occur. But that's a non-generic situation. So good. So the point is, here we don't have to talk about states and whether there are hidden variables and all that. We don't have to muddle your minds with questions of collapse of the wave function. All we need to say is, look, here's my experiment. How do I describe it? Yes?
So if this is an operational point of view, do we ever actually get eigenstates in real lab settings then? That if you're going to base, is that how extreme operational view really is?
What do you mean by get eigenstates?
So can you actually prepare them? So what I mean is the operational view so extreme that we're only basing this on what we see in lab experiments? And in that case, can you actually prepare a state so ideally that you will always you'll be able to predict always what the measurement results?
So that's a very good question. It's a very, very good question. So I would say it depends, but in some sense, you can never prepare a pure state. I mean, this is what experimentalists try to do, and you can come very, very close. And so what you can do is you can make from a principled point of view, there's no fundamental limit to how close you can come to preparing a pure state. But in practice, you have here's why it's impossible to ever validate that you've prepared a pure state. If I say, look, I'm an experimentalist, I prepare this atom in an excited state, I wait 1,000 times its decay time so that I'm very, very confident in the ground state, and then that's what's happening inside this box when I choose some dial setting, and then I press go, and then I confirm that indeed it was in that ground state by measuring that operator. And then I do that again and again and again, 1,000 times, 100,000 times, and I get the same answer. How do you know that my error in the preparation isn't 10 to the minus 9, right? So it's impossible to ever validate that experimentally. But what you can do is you say, look, I know that I'm within a factor of epsilon of preparing this pure state. Then you can do enough statistical tests to confirm that your error is less than epsilon with high probability, assuming you haven't had too many random events, improbable events, right? I mean, things like that. So those are the kinds of considerations that come into play for answering that question. So in principle, yes, you can prepare a pure state. The formulation we're going to give allows for that, but in practice, you only come to within some arbitrary precision of that, just like in classical mechanics, actually.
So it's like a limit of
Yeah. Good. Okay, so that's why I'm using this kind of language for giving the axioms. So an ideal preparation of a quantum system, or I should say can be described by a Hilbert space projector. So now let's look at what this means more concretely. So basically, we start with a Hilbert space. H. How many of you know what a Cauchy sequence is? About half? Okay. So a Hilbert space, H, is a complex, well, in our case it's complex. I mean, there are real Hilbert spaces, but we're going to use a complex one. Linear vector space that is complete in the norm. So complete in the norm, anyone want to rattle that off from memory, what complete in the norm means? Sir?
It means that every Cauchy sequence converges.
Exactly. It means that every Cauchy sequence is convergent. Okay, what does that mean? Okay, this is the infinite regress of mathematics. Okay, well, what that means is that, sorry? Every Cauchy sequence is strongly convergent. How about this? The limit, let's do it, the limit of every Cauchy sequence is an element of the space. Okay, that's what it means. So you say, well, what's a Cauchy sequence? A Cauchy sequence gives you a way of defining the limit of a sequence without referring to that limit already, because we don't know what the limit is. We don't know if it's in the space, so we can't really talk about it. So what we're going to do is we're going to consider, so a sequence of states of vectors indexed by m. Sure. So a sequence that satisfies, I'm going to run out of space here. So if you have this sequence and you take two instances of that sequence and you look at the distance between them, if that distance goes to 0 as m and n go to infinity, then we say that sequence is Cauchy convergent. So this is a Cauchy sequence. So in other words, we didn't say what the limit was. We didn't need to talk about the limit. We just said that, look, whatever this thing goes to, we want the difference between these things to go to 0 as you get close. So they basically converge to something. And then a Hilbert space is complete in the norm if the limits of, so this sequence has a limit in the Cauchy sense. And then we say, well, we want that limit, the limit of that sequence to belong to our space. So it's a completeness condition, just like you see, for example, for the complex numbers, the real numbers. You want the limits of sequences to belong to the set you're dealing with. If the limits of sequences don't belong to your set, then you have holes in your set, and it's not a good situation. So a linear vector space, in fact, an inner product space, is complete in the norm. In fact, this is an inner product vector. This is, in fact, an inner product space. So an inner product space means that in addition to having the vector space structure, we have some inner product defined between our vectors. In fact, that's associated with a norm that induces a norm on the space. So that's this norm. That's what these vertical lines correspond to, is that norm. And so a Hilbert space is complete in the norm if a vector space, an inner product space, if the limit of Cauchy sequences, so I have some sequence that converges to something. I have a sequence that converges to something. Let's call psi that something that it converges to. And now I can ask the following question. Is the object that this limit converges to, is it part of the space I've defined, or is it outside of that space? And so if this is actually part of the space, okay, and then this implies then H is a Hilbert space. Okay, Okay, so that's a very technical condition, which we need kind of for mathematical completeness. Now, it turns out all finite dimensional Hilbert spaces are complete in the norm. So kind of useful fact. All finite dimensional Hilbert spaces all finite dimensional inner product spaces are Hilbert spaces. So if it's a finite dimensional system, we don't have to worry about this distinction. It comes for free. In the infinite dimensional case, it's not the case. So you can have infinite dimensional inner product spaces that are not Hilbert spaces. The ones we use in quantum mechanics are Hilbert spaces. So, example. Consider the Hilbert space H equals CD. This is a vector space. Spanned by vectors of the form 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, all the way down to 1, with complex coefficients. So you have some vector psi, which is an element of this vector space, and then psi can be expanded as a sum over L, CL, EL. I'm using Dirac notation. I assume you're all familiar with that. So here each L corresponds to one of these unit vectors. And the key point is that L goes from 1 to little d. And CL is a complex number. And how do I find CL? Very easy. Yeah, so I have an inner product, psi, actually backwards, I have it backwards. EL psi is equal to CL. So it's a vector space, I add an inner product to it. Yeah.
What is the importance of your space to be complete in the sense of the norm? I mean, can you do quantum mechanics without requiring your space to be complete?
You know, I think maybe you could, but it would get pretty messy, I imagine. I mean, the idea is that then you wouldn't be guaranteed that.
Why do you need complete?
Yeah, I know. That's a very good question. I don't know that I have an adequate answer to that question. But I think that, when you start constructing things, and if you talk about sequences, like we were discussing earlier, this question of what's a pure state. Well, you can imagine it as the limit of some sequence of preparations where you make epsilon smaller and smaller. But now, if we don't promise that we have a Hilbert space, then we don't know if that limit actually belongs to our set. So we have a conceptual gap in describing limits of sequences of valid states all of a sudden might not be a valid preparation. So that's kind of a operational reason why it'd be awkward to not have such objects.
I think you also need it if you do a spectrum analysis of observables, so that you can somehow say that you can expand the states in terms of like state of observable. You need that in order to do that. You need to, I think.
But that only works if your observables are bounded, which
Yeah,
they are.
Okay, fair enough.
Okay, so Okay, so if any of you have some insight into this, this question has come up before in my own mind and from other students, and it's something which I've never really felt I had a satisfactory answer to. Like some concrete example of what goes wrong in your formulation when you don't have this completeness condition would be, I think, very nice. I mean, it might be that it's at such a high level of requirement. I mean, we use all of these properties, like spectral decomposition. There's all of these results from linear algebra that we want to use for infinite dimensional Hilbert spaces. And it might be that a bunch of those results, the formal proof that they're applicable tools, requires an assumption of completeness. So probably things like that crop up in the very basic kind of framework we're using. And if you don't have completeness, then a lot of these results about why I can always, I have a self-adjoint operator acting on the Hilbert space, can I write down a spectral decomposition or not? Well, I assume I can. It might be that implicit in that assumption is that I have a completeness condition. So I'd be very interested if one could pinpoint some examples of the kinds of practical theorems we want to use that might require this implicitly. So, okay, so I'm sorry, this example was a bit sloppy, but let me give you a more interesting example. I mean, this example was so trivial that I kind of didn't spend time explaining it properly, but I'm assuming you're all familiar with finite dimensional vector spaces. I mean, this is really, if you're not familiar with finite dimensional inner product spaces, please review it more fully. Things get subtle when we start talking about infinite dimensional Hilbert spaces. So the space known as L squared, which is a space of square summable sequences, so what that means is I have some vector phi in this space, and I can associate it with an infinite. This is now, so these were finite dimensional column vectors, right? They had, I can't do that. This is, sorry for that. That was pretty sad. Okay, this is infinite. Anyways, I just wanted to say that this has D elements. And this is infinite elements, an infinite number of elements. And we have another vector psi. Let's just call this B1, B2. Then it's an inner product space, which means I have to tell you what the inner product is. Notice that the choice of inner product is non-unique generally. So here we'll choose the standard inner product. In Dirac notation, between psi and phi, is just the following infinite sum over L from 1 to infinity of B, L, complex conjugate, AL. So here overbar means complex conjugation. So that's our inner product space. And in particular, we're going to say that this space with inner product given by this is a Hilbert space. So what I'm telling you it's a Hilbert space is that it's complete in the norm. This is a proven fact. Okay, so now, do you guys know what square summable means in this? So we're not considering arbitrary infinite dimensional vectors. We're restricting to square summable ones. So you guys know what that means? Right. So note square summable. Square summable means that the sum over L of BL squared is some finite number, which in quantum language means it's normalizable. So an infinite vector that's not normalizable is excluded from consideration. So another example is, I'm down to 5 minutes. So another example of a Hilbert space is L2R. Of square integral functions. So this is wave mechanics. Okay, so we're using wave mechanics as a special case of our structure. So here we have some psi and phi. And we give them an inner product. The inner product between psi and phi is defined. Okay, it's a choice. We define it to be the integral over dx from infinity to minus infinity to plus infinity of the complex conjugate of the function psi and the function phi so I could have chosen some different measure for my integral. That's the freedom in choosing the inner product. And we demand that that be less than infinity. Now there's something where I can't remember the details, but I think it's Cauchy-Schwarz. So if each sequence, whether it's in this case of infinite dimensional vectors or in this case of infinite dimensional functions, the fact that it's square summable implies that all the inner products are finite. What is that, the Cauchy-Schwarz inequality? Yeah, so via Cauchy-Schwarz, square summability, the square integrability of each function, psi and phi, guarantees that their inner product is finite via Cauchy-Schwarz. This is guaranteed via, is it Cauchy-Schwarz?
Yeah.
Via the Cauchy-Schwarz inequality. And so this is completing the norm and therefore a Hilbert space. All right, there's another example, but I think you've seen enough examples. I guess I should mention one other thing. I should mention that the Hilbert spaces of quantum mechanics are all separable. Needed for quantum mechanics for quantum theory, both non-relativistic and relativistic, are all separable. Now this is a mathematical term. This is from the mathematical literature. This is not to be confused with the notion of a non-entangled state. Same word, totally different context. Okay, so this is a different, it's the same word, but it's a different meaning. Here, separability is a quantifier of the Hilbert space, whereas separability in the context of entanglement is a quantifier of a particular element of the separable Hilbert space. So you can have non-separable states in a separable Hilbert space because the word just, it shouldn't be the same word, but it is. Here, what separable means is this has nothing to do with entanglement. So do not confuse this. We'll see the other meaning of separable later. What it means here is the fact that all bases, let me just make sure I get this exactly right here. Why am I missing a sheet already? Oh, there it is. No, that's not it. Oh, there it is. Okay, good. All bases, all So here what separability means is that all of our bases are countable. So countable means, of course, they can be indexed by the integers. So there can be an infinite number of them, but it's not a continuous infinity. Is there a question?
Why isn't this requirement included in the axiom?
It should be. So you can insert separable before Hilbert space there if you wish. Well, that was a great question. Where was that from? Yeah, so that's something that I was confused by and then finally sorted out, which I was very happy about. It's very confusing, right? So if I want to talk about the harmonic oscillator, I have all these position wave functions. There's a continuous set. In fact, I was going to end on this little puzzle. There's a continuous set. I have my harmonic oscillator. I have a continuous set of spatial wave functions which I can assign as my preparation of that quantum system. So how is that possible if I'm telling you that the Hilbert space is separable and therefore there's only countable bases? That's part of the answer. He said the position basis doesn't give you an orthogonal basis. Yeah, exactly. So the point is we use Dirac delta functions as our basis of position eigenstates. We use plane waves as our basis for momentum states, but they are in fact not elements of the Hilbert space. So when we do quantum mechanics in the wave mechanics level of undergrad textbooks, you're not actually working in Hilbert space. You're actually cheating. And so this is there's a way to rig the Hilbert space to create something called a rigged Hilbert space, which deals with this problem. So rigged doesn't mean like in the sense of a casino you don't want to go to, but rigged in the sense of like a sailboat you want to sail on, as in it's been rigged, it's equipped, right? So one rigs the Hilbert space. This is the technique of Dirac and I forget who else developed it, but it's basically a trick so that you can still use Dirac delta functions and you can still use plane waves in a way that's legitimate. So we'll maybe touch on that later in a week or two. There's another way to do it so that you don't have to, you can still use Hilbert space, but you introduce a more sophisticated notion of measurement called a projector valued measure, a PVM. And once you introduce, and that the mathematical machinery for that is quite involved, and you need a little bit of measure theory and a little bit of operator theory, and you can do quantum mechanics in Hilbert space as promised by the axiom without rigging it the way that Dirac did. But those are all very subtle technical issues. But the point is this, is that if you want to write down a position wave function, if I have some wave function psi of x, which is in my Hilbert space, and I have a continuous set of these objects, these position wave functions, it turns out that I can always express this continuous function as an infinite sum over basis functions. So what do you guys, when you do the harmonic oscillator, what's the energy eigenbasis? Probably all seen this. Exactly, it's a Hermite polynomial, right? So you have a discrete but infinite set of polynomials called the Hermite polynomials, and they give you a basis for the Hilbert space. So I can write out my full quantum state. sorry, this doesn't have x in it. So this is a complex coefficient, which is the inner product between psi and my Hermite polynomial. And I have a countable set of Hermite polynomials. And this is just something like HL psi.
Probably the fact that you need it to be separable has to do with the fact that the Hilbert space completes, right?
Separability does tie into this because you want, yeah, I mean, the point is we know that we have these these countable sets of basis functions to describe this continuous set of possible functions, and separability gives us that. If the Hilbert space wasn't separable, we wouldn't be able to expand we'd have to have an integral here instead of a sum.
You could, if you had an inseparable Hilbert space, though, you could write it as a sum because only countably many of those inner products with the complete orthonormal basis would be finite.
So you're claiming that even for an inseparable Hilbert space, one can still have this kind of an expression?
Yes.
Oh, that's surprising to me.
Why not? Why inseparable means the orthogonal basis would be uncountably many?
That's what I assume.
Yeah, so
I assume that your bases are uncountable for inseparable.
You have to
Well,
choose subsets.
I'll tell you what, that's interesting. I'm surprised and somewhat incredulous about that claim. So could you provide a reference for me? I'd like to see that.
I'll try. I'll see if I can find the text for the course.
the identity you get with the spectral decomposition with the delta functions is over the continuum of states, the uncountably many, whereas the identity you produce with
Are you talking about spectral decompositions of identity? Yeah, so it turns out when you use the rigged Hilbert space formalism, you can still expand functions in terms of an overcomplete basis. But overcomplete basis, be careful, because we're not talking about Hilbert space basis anymore. We're talking about some other mathematical objects that live in this rigged Hilbert space.
So those can be shown to be equivalent?
Yeah, because the point is here, so this is allowed. And what's not allowed, but what yet we do anyways. Life. All right, so is this kind of an integral. Take my plane waves, and then, thank you, dk. And then, what do I have, some expansion coefficient here, psi k? So I can do this Fourier transform style, and I get a decomposition, and this is an allowed thing to do in the sense of it works, but it's not allowed in the sense that this is not an expansion in the sense of I'm expanding over a basis of allowed states. How many of you can tell me right away why e to the ikx is not in my space L2R? Exactly, right? So you're starting to see some of the subtleties that arise in infinite dimensions. There's an enormous mathematical machinery required to justify what we do in first-year textbooks, which isn't even touched on and takes a long time to sort out. But so these are some of the delicate issues that you should be aware of. Okay, I'm standing between you guys and your lunch, so maybe I'll take one more question.
When you say the Hilbert space is needed for quantum theory or all separable, that means that there are non-separable Hilbert spaces as well.
Yeah, mathematically they exist.
So, so completeness does not.
Well,
Oh, you mean that connection? Oh, yeah. Okay.
No,
Any
but
other questions for that?
Can't you still do all of this in non-separable?
Sorry, could you wait till? Sorry, sir. Could you wait till the end of the lecture to speak? Thank you.
I was wondering, are we going to assume that all of the elements of any Hilbert space we're using is normalizable? Like, are we going to ever have like,
Yeah, I think that's promised by square integrability. Yeah. So sorry, all Hilbert spaces are square integrable. Yeah, that's correct. Yeah, I think. I'm pretty sure. It sounds right, anyways.
Yeah, well, I mean, you have enough products so that, and in the products they find.
Yeah. It is right. It has to be that case. Okay, thanks for your attention.